At Apple, we care deeply about security. For protecting both the user and corporate data, iOS provides a comprehensive approach to security that protects the entire platform, from the hardware and OS to services and apps. We've seen businesses of all types, all over the world, that have been transformed by iPhone and iPad. Enterprise workforces are increasingly mobile in response to the need to shorten business cycles, increase efficiency, and get closer to customers. To be productive while mobile, users are bringing their personal devices and applications to work. Users also need always-on connectivity, with secure access to critical business data held in back-office systems. IT recognizes that they need to establish a security policy that balances the protection of company data with preserving a great user experience. In contrast, the traditional approach to IT security, built up over many decades, was all about PC systems and not designed for mobility. This is because hardware and software were built on an open architecture designed to add, upgrade, and swap components easily. But this also made these systems an inherently insecure environment, more vulnerable to various types of attack. As a result, PC operating systems required IT departments to purchase additional third-party security products, such as firewalls and antivirus applications, which increased cost and complexity. Most notably, productivity features that presented any degree of security risk were simply disabled. Company devices were also entirely tracked and monitored by IT in a way that interfered with user privacy. We started fresh with iOS to completely reconsider some of the engineering decisions made in the past. In taking a new approach to security, we designed iOS to address the security issues inherent in a PC environment and built advanced security into our products from the ground up to address the needs of a mobile landscape. A new level of security that's built in, not bolted on, is made possible because we control the hardware, software, and services. We've also solved the need for granular control over work data, while at the same time respecting user privacy and protecting all data on the device, both work and personal. And most importantly, we've done this in a way that's in balance with a phenomenal user experience. Two key aspects differentiate the Apple approach to security. First, iOS devices are secure by design, meaning that end-to-end security is built in from the ground up and integrated throughout the hardware, software, and app ecosystem. iOS protects not only the device and its data at rest, but the entire ecosystem, including everything users do locally, on networks, and with key internet services. Also, iOS devices provide employees with the freedom to work, allowing them to be more empowered and productive within the organization, while respecting their privacy. Let's take a look at what we mean by secure by design. Apple takes a comprehensive approach to security, which means thinking about security at every point, from the system itself, to the data on the device, and the network, right up to the apps that are created and installed. We've thought deeply about security, and as a result, iOS devices aren't only secure by design, but also deliver a great user experience at the same time. First, let's talk about system security. By holistically considering the hardware, software, and services that go into each product, Apple is able to deliver advanced security technologies in a way that makes them simple or transparent to the user. The built-in security features of iPhone and iPad offer numerous examples of this tight integration, including processes that ensure the secure startup, activation, and update of the operating system software, as well as features that protect and authorize the device. In addition to the cryptographic acceleration and unique encryption keys stored in an iOS device's processor, a hardware root of trust is built into every iPhone and iPad. This provides a secure, trusted platform on which to establish the integrity of the operating system. When an iOS device is turned on, its application processor immediately executes code from read-only memory known as the boot ROM. This immutable code is laid down during chip fabrication and is implicitly trusted. The boot ROM contains the Apple root CA public key, which is used to verify that the low-level bootloader (LLB) is signed by Apple before allowing it to load. This is the first step in the chain of trust, where each step ensures that the next is signed by Apple. When the LLB finishes its tasks, it verifies and runs the next stage bootloader (eBoot), which in turn verifies and runs the iOS kernel. This secure boot chain ensures that the lowest levels of software aren't tampered with and allows iOS to run only on validated Apple devices. A failure of the boot ROM to load LLB on older devices or eBoot on newer devices results in the device entering DFU mode. In the case of a failure in LLB or reboot to load or verify the next step, startup is halted and the device displays the "Connect to iTunes" screen. This is known as recovery mode. In either case, the device must be connected to iTunes via USB and restored to factory default settings. The startup process just described helps ensure that only Apple-signed code can be installed on a device. To prevent devices from being downgraded to older versions that lack the latest security updates, iOS uses a process called System Software Authorization. If downgrades were possible, an attacker who gains possession of a device could install an older version of iOS and exploit a vulnerability that's been fixed in the newer version. On a device with an A7 or later a series processor, the Secure Enclave coprocessor also uses System Software Authorization to ensure the integrity of its software and prevent downgrade installations. We'll discuss Secure Enclave in more depth later. iOS software updates can be installed using iTunes or over-the-air (OTA) on the device. With iTunes, a full copy of iOS is downloaded and installed. OTA software updates download only the components required to complete an update rather than downloading the entire OS, improving network efficiency. In addition, software updates can be cached on a local network server with the caching service on a Mac running Mac OS High Sierra with content caching turned on, so that iOS devices don't need to re-download the necessary update over the internet. They'll still need to contact Apple servers to complete the update process. During an iOS upgrade, iTunes or the device itself, in the case of OTA software updates, connects to the Apple Installation Authorization Server and sends it a list of cryptographic measurements for each part of the installation bundle to be installed, for example, LLB, eBoot, the kernel and OS image, a random anti-replay value, nonce, and the device's unique ID, ECID. The authorization server checks the presented list of measurements against versions for which installation is permitted and, if it finds a match, adds the ECID to the measurement and signs the result. The server passes a complete set of signed data to the device as part of the upgrade process. Adding the ECID personalizes the authorization for the requesting device. By authorizing and signing for only known measurements, the server ensures the update takes place exactly as provided by Apple. The boot time chain of trust evaluation verifies that the signature comes from Apple and that the measurement of the item loaded from disk, combined with the device's ACID, matches what was covered by the signature. These steps ensure that the authorization is for a specific device and that an old iOS version from one device can't be copied to another. The nonce prevents an attacker from saving the server's response and using it to tamper with the device or otherwise alter the system software. Keeping system software up to date is part of good security practice, though with other platforms it's often problematic or sometimes impossible to do. Apple leads the industry in delivering operating system updates to provide new features to users, as well as to address emerging security concerns. These free updates are provided for all supported devices simultaneously. Users receive iOS update notifications on the device and through iTunes, and updates can be delivered wirelessly, encouraging rapid adoption of the latest security fixes. By setting up a device passcode, the user automatically enables data protection. iOS supports 6-digit, 4-digit, and arbitrary length alphanumeric passcodes. In addition to unlocking the device, a passcode provides the entropy for certain encryption keys. This means an attacker in possession of a device can't get access to data in certain protection classes without the passcode. The passcode is entangled with the device's UID, so brute force attempts must be performed on the device under attack. A large iteration count is used to make each attempt slower. The iteration count is calibrated so that one attempt takes approximately 80 milliseconds. This means it would take more than 5.5 years to try all combinations of a 6-character alphanumeric passcode with lowercase letters and numbers. To further discourage brute force passcode attacks, the iOS interface enforces escalating time delays after the entry of an invalid passcode at the lock screen. Users can choose to have the device automatically wiped after 10 failed passcode attempts. This setting is also available as an administrative policy through Mobile Device Management, or MDM, and Exchange Active Sync, and can also be set to a lower threshold. On devices with a Secure Enclave, the delays are enforced by the Secure Enclave coprocessor. If the device is restarted during a time delay, the delay is still enforced, with the timer starting again for the current period.